Let's go back into the textbook for a little bit and catch up on systems of nonlinear equations. How we can take a couple of these methods we previously just discussed and apply them to more than one equation at a time. That's probably the more commonplace engineering solution when you have multiple equations describing multiple dimension problems, when technically you have as many equations as you need to solve for the number of variables, but if it's nonlinear, you can't use matrix algebra to solve it, and cool, pull out MATLAB, let's solve it this way. As one example, they provide equations 338 and 339. They'll be stepping through those. Those are two functions of x and y describing the graphics shown on the left. One's an ellipse, one's a catenary. Fairly basic equations, pretty easy to solve, easily differentiable. So the first method is how we're going to take the Newton method and apply it across any number, at first just two, but then we'll broaden it to n-dimensional solution methodologies. I'm just going straight from the book here because they have a nice layout and discussion. We will broaden one of their points I gloss over too fast, one of those left to the reader type moments. Anyway, starting rule, setting up the equations in the form where they equal 0 still stands. You might see on the initialization here, the initial form of that problem, especially equation 2 was the more generic elliptical form, but they've modified it down here, go ahead and multiply things out through a common denominator to make it equal to 0. So these are already modified into the functional forms equivalent to 0, just like you would with a single dimensional Newton problem. So 338 and 339 are ready to go. That's step 1. Just do the functional transformation. Step 2, Taylor series expansion. In fact, you don't actually have to take the Taylor series expansion of these functions every time you want to do a multi-dim solution with the Newton method. This is just where the method is derived from. So, as I alluded to when we were discussing Newton method, we will start by throwing out the higher order terms. We're satisfied with this method's efficacy if it can simply just move us toward the better solution without in one step taking us all the way to it. It's worth the simplifications. So let's look at what is left. So the approximation, the two-dimensional approximation of the first function requires, of course, the departure point, the functional value at x1, y1. That's where you're at. x2, y2 is the true solution. Keep in mind this whole set of equations, 341 and 342, are just estimates. So you start with the functional evaluation at your guess point. x1, y1 is where you've guessed. x2, y2 is supposedly moving you in a better direction. So every time you see x2 minus x1, that's really just a delta x value. That's the step size you're taking in the x direction. Of course, since this is two-dimensional, we deal with partials in the Taylor series expansion. So we multiply that by the partial of function 1 taken with respect to x. Then to complete the first term of that Taylor series expansion, it's the delta y term, the distance you're moving in the y direction, times the partial of the first function with respect to y. Of course, you repeat these same ideas and processes for the second equation. Just all the f1s are replaced with f2s. And this is really building up to a system of equations. Because something very useful happens. If you assume that this equation reasonably represents a movement towards the true solution we're seeking is 0. So if you plug in 0 for the functional value at x2, y2, for both of these, the left-hand sides become 0. We can apply a simplification now by moving our starting points over, thus making them negative. And we arrive at equations 343 and 344, which now you're just one step away from having this theory developed. So again, the step from this set of equations to the next is that the functional values at x2, y2 become 0. These are non-zero because that's your initial guess point. You're not depending on being lucky enough to guess the perfect solution in a system of equations. So those are non-zero. Move them to the left-hand side, make them negative. But now look what's left over here. This looks conspicuously like a matrix form problem. Two equations, two unknowns, the unknowns being delta x and delta y. You don't know how far you have to move away from your guess location, x1, y1, to find the actual root values that are 0, the x2, y2 locations. So this leads us to a matrix formulation, and where I want to go over to surface writing. So let's look at what we have left. Let's take equations 343, 344, so leave your textbooks open, reference that. It's page 82 in the 3rd edition. But let's put this into matrix form so you can see exactly where we're going from this point. So if you have df1 dx. That's the first top left coefficient. You have del f1 dy. Top row right coefficient d f2 dx df2 dy. That is actually the coefficient matrix. So it's just the partials with respect to x and y of the first equation, partials with respect to x and y of the second equation. The solution vector we're looking for is delta x, delta y. And the solution vector is, well, those are the unknowns. I should say the solution vector is now negative f1, our guess at x and y, negative f2 at x and y. So, that's a matrix problem. Technically, all you have to do is invert the coefficient matrix, multiply by your solution vector, which is over here. Of course, those are just our guesses, which is kind of weird. You think in this case that you're going to have multiple guesses that end up finding the right delta x and delta y, but still you have a delta x, delta y depending on the guess values, so I suppose it makes sense. There's also a nice thing. There's a name given to this left equation. Jacobian. We didn't just study that and expose you to it for the first time for funsies. That's what we're looking at. And in fact, the textbook prefers a different solution methodology than invert and multiply. Though perhaps sometime in the future we'll try that for a small matrix. They employ Cramer's rule. So if we go back to the textbook and look at equations 345 and 346, which are unfortunately on different sides of the page, but they are of the same family and style, you will notice that of the Jacobian determinant on the left-hand side, if you remember Cramer's rule, if I can put it in general form back on the surface, it's that you take the solution vector, substitute it in to where you would otherwise have A12 and A22. Substitute in for the left column if we're going for x. And down here you just have the determinant of the modified matrix up top, determinant of the unmodified A coefficient matrix on bottom. That's how you find out the solution vector. This would be delta x because it's the first variable. So if we look in the textbook, and if you remember what our initial default state is here, our solution vector is going to be negative f1 and negative f2. So really for the first solution, I'll just write it in here, negative f1, negative f2, determinant of the unmodified matrix. Well, just to make sure you're clear, this is what we're calling the A matrix of coefficients. It's also known as the Jacobian only because it's a matrix of all of the partial derivatives. The determinant of the Jacobian, so what's happening down there on the bottom, this is a modified matrix where instead of just A12, if you want a more explicit definition, that'd be del f, del y. This is del f2. That was f1, del y. That gives you the solution for x. So if we look back at the textbook, oops, this one, you see that's exactly what they've done. Delta x solution, this is them already multiplying out the determinant of a 2 by 2. So the top left times the bottom right minus the top right times the bottom left. Notice the top right has a, I suppose it would be the top right has a negative sign. It'd be the bottom left one has a negative sign. One of them did, and it flipped the sign in the middle. That's why you don't see the minus sign. It turned it back into a plus. And then the bottom is just the Jacobian determinant of the matrix we see described up here. So that is how you solve for delta x. And delta x is an imperfect move towards 0, but it is a good move towards 0. And this is essentially what our iteration scheme becomes. So it's kind of hilarious. All the real work is done in 346 and 345. Those two equations do the heavy lifting. However, 348 is where you actually take the move and the step towards the next improved station. So that's Newton's method in multiple dimensions. You, of course, iterate, and each iteration should move you in the right direction as long as you don't encounter one of those unstable Newton methodologies that we covered in the one-dimensional case. Those still can apply, perhaps even are more likely to apply in a multi-dimensional state. Now here's what's interesting, is that you can expand this same type of theory. You can scale it up to any number of dimensions. So as long as you can express each equation in a form that equals 0, which shouldn't be too terribly difficult, you find the Jacobian of that system of equations. Notice that's still the same format we were used to seeing in the previous problem. That large matrix is known as the Jacobian matrix. It's the derivative of each possible dimensions, x, x2, x3, x4, xn, of function 1, second row is function 2, function 3, so on and so forth, however many functions you have. The deltas are the movements in each dimension, and the f's are the functional values at your guessing points for each dimension. So, and then the update is actually just trivial. It's again just taking your guess, moving the steps that you've calculated by solving for this system of equations. Again, at that scale, I would probably suggest inverting the Jacobian, multiplying by your guesses to find that larger list of delta x's. So, like we alluded to, most things just get reduced down to a large matrix problem, and now you can solve, as long as it's stable, any number of nonlinear equations in any dimensions. Pretty nifty, pretty powerful stuff. While we are here, it's worth also noting, the book goes through it relatively quickly, and we will too, that it is possible to use fixed point iteration for systems of equations as well. If you remember, fixed point iteration is just where you rearrange the equations. Instead of being equivalent to 0, as every other system seems to use, we make it equivalent to x. There are multiple ways to do that. Some of those formulations may be stable, some may be unstable. What's nice about using this method in multiple dimensions is that it's just as complex as a single dimensional case. It's not any more challenging, no more difficult, just maybe a few more calculations or whatnot, but there's no Jacobian, there's no inversion, it's just the updated equations are readily available. The downside is you still have all the same stability criterion that the fixed point iteration method is subject to. So there are 3 equivalents to the stability criterion given for the single dimensional case. First requirement, that the functions g, those are your solution iteration functions that are dependent on x instead of 0, are continuous in the neighborhood of the solution. They can't jump around, they can't suddenly change values, they cannot be discontinuous. Yeah, you know what continuous means. Second criterion, and this one is probably the more challenging one to determine if you want to be rigorous about ensuring convergence, that the partials of each g function, the summation of the partial derivatives, more precisely the summation of the absolute value of the partial derivatives in every dimension of the function is less than 1. So now if you have a certain gradient in x and another gradient in y and another gradient in z and another gradient in a, b, c, however many dimensions you have, the total absolute value of the partial has to be less than 1, or you're not going to converge. So this makes that system even less likely to be convergent in multidimensional form, but it could still work, and if it does, it's very, very simple. And then again, okay, so the initial guess is sufficiently close to the solution. Thanks for that. What does sufficiently close mean? They don't tell you. It's different for every problem. So that's like a criterion that actually doesn't help you at all. The biggest help here is criterion 2, knowing that the absolute value of all the partial derivatives summed together have to be less than 1. That's the one to pay attention to. And we'll go probably next into an example, which I'll separate into a separate video for your convenience.